All right, let's jump right in. Today, we're going to tackle a classic structural analysis challenge, one you definitely see in a university course. Our mission? To take this really complex-looking portal frame problem and break it down step by step using a super powerful technique called the method of influence coefficients. So here's our game plan. First, we'll get a handle on the problem itself. Then we'll get to the main event, building something called the stiffness matrix. After that, we'll calculate all the little pieces that go into it, solve for how the frame actually moves, and finally, we'll get to the big reveal, the forces inside the structure. Okay, so first up, before we can even think about solving this thing, we've got to really understand the challenge we're facing. So here it is, our starting point. What we have is a portal frame. It's 5 meters high, 10 meters wide. And you can see there's a 50 kilonewton force pushing it sideways at the top. So the big question is, what happens next? How is this thing going to bend and move when we apply that load? So this is the crucial first step, and you got to get this right. We have to figure out what we don't know. Now, the problem tells us to ignore any stretching or squishing in the beams themselves. So that leaves us with 3 key unknowns. First, how much does the frame sway sideways? We'll call that delta. And second, how much do those top corners, B and C, actually rotate? We'll call those phi B and phi C. These 3 things, they're the key to unlocking this whole puzzle. Now, how are we going to find those unknowns? Well, we're going to use a really systematic approach called the method of influence coefficients. It's basically a way to figure out how a little nudge in one spot affects the forces everywhere else. And using this method, we can build what's called a global stiffness matrix. You can think of it as our master key. Think of this matrix like the structure's DNA. For this problem, it's a 3x3 grid of numbers, and it contains all the rules that describe the relationship between force and movement. It tells us exactly how much force it takes to make the frame sway a certain amount, or to twist a corner. If we can just build this matrix, the rest of the problem basically solves itself. Right, so how do we actually build this thing? Well, you don't do it all at once. We're going to forge this key piece by piece. We'll figure out all the values inside the matrix, the coefficients, by looking at 3 separate, much simpler scenarios. Let's start with case 1. Imagine this. What if we push the top of the frame sideways by exactly 1 unit? But, and this is the important part, we magically stop the corners from rotating at all. They have to stay at perfect 90-degree angles. So, what forces would it take to do that?
And what's so cool about this slide is it shows us the answer. We use these free body diagrams, where you isolate a piece of the structure to see all the forces acting on it, and they let us calculate the internal forces needed to resist that 1 unit sway. The numbers we get from this, that's the entire first column of our stiffness matrix, just like that.
All right, case 2. We hit reset. This time, we lock the frame down, so it absolutely cannot sway sideways. Instead, we introduce a perfect 1 radian rotation only at corner B. Corner C stays completely locked. And yeah, you guessed it. Just like before, this analysis tells us exactly what forces and moments are needed to create that specific twist at joint B. The results from this calculation, well, that gives us the second column of our stiffness matrix. See the pattern here? We're just building it up, 1 piece at a time. You can probably guess what's coming for our final case. We do the exact same thing, but on the other side. The frame is locked, no swaying, but this time we apply that 1 radian rotation to corner C, while B stays perfectly still. And there it is, the final piece of our puzzle. The forces we calculate here, the ones needed to make that isolated rotation at C happen, they give us the third and final column of our matrix. So after breaking down those 3 cases, all the pieces are finally in place. What you're seeing here is our complete global stiffness matrix, but in its symbolic form, with all the L's and E's and I's. It represents all those force displacement relationships we just uncovered. This is the key we've been working so hard to forge. Okay, so we've got the theory down. Now it's time to translate that into actual practice. We take those formulas and we plug in the real numbers for our frame, the lengths, the material properties, all of it. And that gives us the final numerical version of our stiffness equation. This is it. We have our equation all set up. We've got our known forces on one side, our unknown displacements on the other, and our brand new stiffness matrix connecting them. It's time for the big moment, solving for those unknowns we talked about way back at the beginning. So how do you solve a system of 3 linear equations like this? We use a classic, tried-and-true mathematical procedure called Gaussian elimination. As you can see here, it's just a really systematic process of adding and subtracting the rows of the matrix to simplify it, step by step, until the answers for our unknowns just pop out. And boom! Here are the results. After all that work, we've found exactly how the frame is going to move. It sways sideways by just under 2 millimeters, and both corners rotate inwards just a tiny, tiny fraction of a radian. We've officially solved for our unknowns.
But hold on, we're not quite done yet. Because knowing how the frame moves is great, but it's really just a means to an end. It allows us to calculate the final, and maybe the most important part, the actual forces and stresses inside the beams and columns.
And this right here is the ultimate payoff. These diagrams are everything. The M diagram shows us the bending moment, and the V diagram shows the shear force at every single point in the frame. For an engineer, this is the gold. It tells you exactly where the structure is under the most stress, and that's what you need to know to design it safely.
So, what's the big takeaway from all this? Well, even though we just walked through a single homework problem, the fundamental ideas we used, influence coefficients, stiffness matrices, these are the absolute bedrock of modern structural analysis. The very same principles, just scaled way, way up with supercomputers, are used to make sure that the skyscrapers, bridges, and stadiums we use every single day are safe and sound.